Real time, I have adjusted my presentation to do the short version, so you will have your break. How's that for dynamic adaptation? Okay. So that being said, we'll see if this works. It should. I have no dynamic servers or motion software. It's just PowerPoint, so it should work perfectly. So in the next 25 minutes, what I hope to share with you is a window into something which is, I think, very exciting, because it takes something which is old and dingy, or at least routine to us, and gives it new life, gives it tremendous utility and statistical, dynamic, diagnostic, precision power to alter clinical care, and at the same time spend only the money of electrons. How's that for a deal? Just spending electrons as opposed to more lab testing. And by that I mean encoded data in the routine laboratory data that we're already ordering on a routine basis. As just by background, I have nothing to disclose, although has been mentioned multiple times during this conference. Be happy to change that. So let's look at a simple thought experiment. Some letters. I had to use Courier fixed font so that things would line up. There's encoded data in here. Imagine that these are simply lab values. It could be CTAG as well. You see anything right now? And of course, this is not a test of you specifically, but more of a demonstration of the human cognitive system. Do you notice any words? It's kind of like a crossword puzzle. In fact, it is a crossword puzzle. See anything? Anybody? Raise your hand. I'll give you a clue. I did it vertically to make it hard. Do you see it? Okay, so we have one person. So we have one, like 5, 6 sigma gifted individual, and the rest of us mere more. Okay, 2. Okay, so I'll give you a little help. We'll do that. Do you see it now? Okay, even when I make it obvious, it's hard. And if we do this, we put like our beer goggles on, and we can see it. Hello, world. So with that as a pretext, we'll do a little bit more complex experiment. ECG, EKG. As I remember from medical school, up, down, very, very fast. It's one of the residents who taught me. Do you notice anything else about that besides VTAC? It's actually a very quick diagnosis if you recognize it. Torsade, exactly. And of course, the key point to recognize here is not only is there the up-down, but there's a different component, the longer length scale, which is a twisting of the axis, which is like a party streamer, as some people have described it. And that requires you to sort of step back and say, oh, the long-term amplitude is changing. That's encoded data. And we see this analogy in other continua. Oops. Let's go forward. So I think it's fair to say that human cognitive process excels in interpretation of discrete data. In clinical pathology, we do this all the time, looking at individual analytes. We actually can do this quite well, up to an N of 5 or 10, and then our performance starts to decay. By show of hands, how many of you saw the presentation, I guess yesterday, by Drs. Anand Digay and Barron from MGH? So the beauty of that is it's available, of course, online. It's a wonderful pretext to some of the additional derivative type information I'll show today, and I'll just reference some of their background information, for example, in describing machine learning algorithms. But both their presentation and my similar assertion is that as complexity level of data increases as far as presenting to the human being, 2 things happen. As a possibility, the total amount of data that is encoded in the discrete data goes up geometrically as a result of the linear size of the data. And there's statistical theory actually from enthalpy and entropy of information theory that defines that, whereas the noise goes up as a square root of that, the so-called shot noise, which indicates that, interestingly, as your data set size grows larger in terms of number of variables, the number of n you need to validate that, parenthetically, goes up geometrically as well. So the bad news is, yes, there's encoded data, but in order to mine it out, we're going to need more and more samples. So there's an argument for pooling of resources, pooling of sites, and I'll get to that in a minute. And then the second observation is that our potential to extract this data really diminishes with the degree of dimensional growth. And I would posit to you that we've already blown the limit with when you combine a CBC and a Chem 20 for what's actually in there. Maybe, adding maybe patient age, gender to that as well. We've already blown the limit. So as a hypothesis, if we can say that there might be, let's say, distinct and medically actionable diagnostic information already distributed throughout multidimensional parametric data that we already acquire in addition to the obvious data. So we already know this. We know patients with chronic liver disease, you don't just look at the transaminases and the ALT, the SGOT and the GGT. You look at it all together, and that becomes an experiential thing. You don't really know why this particular set of analytes bothers you more than others, but based on your experience, you know that this patient is probably going to have a worse clinical trajectory. And that is, in fact, extraction of encoded data. But our ability to do that becomes increasingly difficult as the number of parameters increases. So in point of fact, we're probably leaving a lot of information on the table. In fact, I know we are. And so also the corollary of that is that the consistent extraction and interpretation of such data, in fact, may be unreachable by the limits of human cognition, owing to both complexity and subtlety of the distribution of this data. So that's not to say all complex data sets will have such encoded data, but many will. In fact, we've already found a number of use cases, and I'll show you one particular exemplar that I think is quite illustrative of this opportunity. And we have other use cases that we're testing that could suggest with a CBC and a Chem20, just as an exemplar, there could be as many as 10,000 diagnoses that are of high precision, high precision. They can be mined out of these simple numbers with the appropriate statistical models, which is really quite transformative. So as, if we look at the human cognition space, just to summarize, it's an adjacency problem. Well, there's no adjacency with a single data point. It is what it is, and you can make the diagnosis right away. It's not a problem. So if I showed you that, as you're a clinical pathologist, you've got a differential diagnosis of 2. What is it? Lab error or? Really, somebody injected accidentally a KCl wash in the patient. So, medical emergency or hemolysis or lab error. Okay, and so worst case scenario, if somebody puts, NGS sequence, here's your 4 billion base pairs. What's your diagnosis, doctor? It's not going to happen. So that's the problem. So that's, of course, the extreme ends of the spectrum. In terms of a data adjacency problem, then you have parallel problems in terms of aggregated data that may not be related to each other, and then spatially encoded. For example, like that letter example, time series data, for example, the EKG I showed you, and the distributed data, where you have an n-dimensional set of either time series or single time acquired parameters, and there's subtleties that you can't tell cognitively that absolutely correlate with one or more diagnostic entities, or any combination of the above all of those. So if we look, for example, just at the reference intervals of some of the routine, commonly measured analytes in the millimolar, milliequivalent range, you can see right away there's a problem from a cognitive perspective if we're interpreting numbers, because they're not all 0 to 5, 0 to 10, 1 to 10. They're all over the place. And we in our minds have to carry out some type of linear normalization in comparing one number to another number, knowing that some numbers are extremely well regulated, some have a broader range, some have different starting center points, means, medians, and so forth. And this, as you multiply the number of parameters, just for routine blood indices, CBC, Chem20, other analytes, it becomes an interesting cognitive challenge of mining all the different possible data that might be present. Let's extend this analogy now in the context of personalized and precision diagnostics, which from everything we've heard during this meeting, we know is coming. And the hope is that when it arrives, it will be stewarded by ourselves within the collective fields of laboratory medicine and pathology, and not by interlopers, as I would call them. And I do mean that pejoratively. So the idea then being, if we have all these different kinds of data, which you'll notice are on different length scales, different components of the central dogma or model of biology, biochemistry, and different analytes, different measurement classes, they have often have a common element, though. They're composed of poolings of discrete data. And whenever you see that collective property of poolings of discrete data, you have the opportunity for encoded data. So this is a general class problem which then would indicate if you can pull encoded data from one data class type, something as mundane as a CBC, Chem20, patient age, gender, weight, then you can pull it from larger classes or combined or pooled classes of data. So as a central thesis statement, how are we doing time-wise? Okay. We have existing routine laboratory data results. Let's hypothesize that they do have. We don't know this a priori, but we hypothesize that they do have encoded data, which may be in fact novel and independent of each diagnostic data. Now, I'm not going to put any Fourier transforms or anything on the screen, but we know from Fourier transform theory, this concept of orthogonality is real, that you can have one data point that affects every other data point in that Fourier transform. And similarly, you can have an encoded piece of information that's in essence in every single data point in a Fourier transform that can map to a single data point. That's mathematically been proven to be absolutely correct. So to extend this thesis to biological indices makes perfect sense mathematically. Now, going to the other end of the spectrum, what's in practice, let's just look at the lowly LIS. Do we have any mechanism in the LIS to capture such data? In the LIS itself, no. Or to easily reproduce such capture across disparate systems? No. Or get the input data electronically? We can certainly print results from a lab system and you could type them in and get half of them or a third of them wrong when you go to the new system, but that's not an ideal or optimal interface system. We don't have that capability as a general rule. They're all custom made on demand. Or the ability, once you've generated ostensibly such a integrated, extended encoded results, to forward those to downstream repositories or the original requesting providers. So large gaps in our current LIS repertoire to do this kind of thing. So we'll get back to that. But let's look at the exemplar itself that I'm going to use to show you how encoded data can actually be clinically relevant. So Crohn's disease and thiopurine testing. So there's an indication for patients on long-term thiopurine and 6-MP therapy. They need to be tested as chronic illness periodically because of several eventualities. There are metabolites that can be tested. It's actually expensive testing. I'll get to that. Interestingly, 0.3% of the population, individuals cannot properly process the active form, leading to severe hepatotoxicity. This is bad. You want to know that because what you're going to do, you're going to try something else. You're going to stop the drug. The remaining population exhibits a log normal distribution of metabolic response, which means pretty much every single person you want to monitor and titrate their treatment so they can be in the optimal range in terms of level of metabolites, which is the indirect method of showing appropriate blood levels of the indirect and the direct form of the drug. And at least as a few months ago, although there's been some interesting Supreme Court rulings in terms of what is natural art algorithms that can be patented or not, Prometheus Laboratories has been the sole source provider of what is approximately $200 to $300 test, which needs to be ordered every few months. There's their website. They have information for both physicians as well as patients. And again, they offer a good test. It has reasonably good sensitivity and specificity, but not 100 or 99% for 99 sensitivity specificity. It's less than that, and I'll show you that. Over the past decade, past 12 years, there's a good body of literature that suggests that this testing is predictive of good outcome, so it's justified. Although the literature also shows that there's still a cohort of patients that don't correlate with the testing. So enter a change agent or perhaps disruptive technology. My colleague at the University of Michigan, Dr. Peter Higgins, he's a gastroenterologist. He's also a machine learning specialist and was curious about whether or not it was possible to extract more information from routine indices as opposed to sending a blood test off for a $250 test every 6 months. And the short of it is, not only does it works far better, and it gives you more information than a molecular test. So you'll notice across here are 3 general classes. Let's see if the laser works. It does. Yep. So the top class is the algorithm overall response rate. versus the actual testing response rate, you notice that there are 3 classes for the algorithm, just 1 for the clinical testing. So if this is the ROC curve, this is, of course, randomness. So this is the area under the curve. These are ROC characteristic operation curves of the quality of the test. And you can see that the AUC, or area under the curve, for the calculated algorithm, based on CBC Chem 20 and patient age and gender, is significantly better than a bench-based test. And the curious thing about this ROC curve, no lab testing was done whatsoever. It's simply taking a bunch of numbers and putting it through a machine learning algorithm, 10,900 decision rules, which are basically in the family of if the hematocrit is this number, higher than this number, then look at the MCV and so forth. And branching, imagine every sequence branching possibility for those 28 or so algorithms, and you can see that the tree size gets very large, except it's highly repetitious, and they're simply weighting cutoff threshold values. The trick with this type of algorithm is having a computer do it, because if you're doing it with a calculator or with a spreadsheet, I can guarantee you're going to make a mistake sooner or later. This needs to be in a computer. And the challenge is as well, it's based on the reference intervals for the source lab. I'll get to that in a minute. The middle curve here is something that's not available from Prometheus. It can tell you if the patient is compliant. Based on a prospective longitudinal model, the pattern of analytes in the blood correlates very tightly with historically verified compliance with drug administration or a patient taking the medication. And finally, the third is shunting, identifying quickly if the patient is one of those 0.3% population that is easily into the hepatotoxic range. Again, all of this done without any additional bench testing. In addition to the decision rules, there's some clinical rules for branch points when to start or stop therapy. These can be basically based on clinical indications along with the test output, generating nothing more than a simple suggestive text paragraph, which needs to be provided to the clinician. You could certainly respond with the raw numbers to the clinician, but you could see immediately with a simple rules decision tree, you could convert the combination of the shunting of the response as well as the overall metabolite level to a set of indications that could be recommendations that could go to the clinician. This could also live in the LIS, so the LIS output itself could be clinically actionable information. Here's a little bit larger inset, so you can just see the analytes that are involved in this calculation. Nothing exotic. Again, the area under the curve for these ROC families, 0.59 with, again, a molecular-based test, 0.85 with the p-value being well below 0.001. So, and this has been reproduced now in 3 successive studies, 2 subsequent publications, and 2 other sites in addition to my colleague Peter. So quite compelling. And again, when I first saw these, I was astounded because you would expect this to be associated with some type of precise molecular test or molecular test with an associated rule set. And to see that this is simply based on calculations is quite compelling. This has resulted in our collaboration between pathology and gastroenterology. We just received an award after a year of the initial notice award for an R01, which is going to allow us now to try making this type of technology available to anyone who's interested. The challenge, of course, is it's not a typical type of collaborative arrangement where you want to share lab specimens. And it's not that. That's actually easier. You put them in the mail or you put them into your courier service. We have to share data. God forbid. How are we going to do that? So, I mean, the core model is actually very simple. Data source, which is a plurality, to the core LIS, then a rules engine, back to one or more core LISs, and then you have this plurality of consumers. So it's both a pipeline and orchestration challenge. And so besides the opportunity of encoded data, you have the added burden of now being able to shuttle data into a system, because now your input parameters or your input is no longer a test tube. Your input is data itself. That's different than the usual laboratory testing model. And your output is data. That's a little bit more routine. But given the fact that this might serve in the capacity of a reference lab, you have to now have, from a multitude of input sources, a very rich way of getting the input parameters for that CBC and Chem 20. So enter a possible solution. Again, I have no interest in this company. We're simply using the Ripple down from Pacific Knowledge Systems because we've identified it as the best solution. We had to come up with a clinical grade rules engine that would allow us to put in upwards of tens of thousands of rules. And it's not just a matter of the system having the requirement to be performed quickly. That's a given. It has to perform quickly enough so that it can be part of the overall LIS pipeline. It has to be easy to configure and maintain, because once you have these tests up and running, there's almost a total expectation that the discovery will mean you have to optimize and tune the parameters on an ongoing basis. Here's an interesting property of that particular platform. It's actually very easy. It's linear with effort. As the number of rules increase, and this goes to 10 or 10,000 rules, the level of effort stays the same. It's based on a very elegant interface, very appropriately designed tool, which was made specifically for very complex systems like this. Just pure serendipity that we found a tool that was so well matched to an algorithm that would require more than 10,000 rules. So a common deployment model that we have, we've done this internally, and we're looking at ways of externally bolting it to multiple other outside sources. You have the request entry of original data goes into the LIS, which itself would be the request along with the original lab data. And see, we're not sending test tubes, we're really sending results. We want as the input results, and that's mapped against a previous database if you have them for comparison, so you can do time series analysis. All that is shuttled to the Ripple down server that applies these tens of thousands of rules using a clinical knowledge base that I described you in that decision tree to, when you have your numerical answers, to append to it the appropriate text response, validation if you so choose, a person looking at it to make sure it's not a crazy result before going back, and then the interpretation message goes back to the LIS. And normally you'd be done, except if the originating source was far, far away, you're still not done because now you have to find a way to get it back to the originating source. And then you have an enhanced pathology report that has both the raw data, the CBC and the Chem 20, for example, and this really sophisticated molecular type test that had associated with it no actual molecular bench testing. It's kind of a surreal world, but the ROC curves don't lie. And as you discover more about the correction given by the pathologist, no, this isn't quite right, that goes to a knowledge builder, again built in Ripple down, that lets you fine-tune the tools in real time. So as the pathologist corrects reports, you at the same time further educate the database. It gets better as you use it. In terms of that clinical decision support rules, again, the Ripple down server adds the critically important component of putting in the clinical interpretation based on the combination of the three parameters that we receive. That removes a significant amount of work. And in terms of maintenance, it's actually done at an encoded data level, which makes it much easier than having to deal with raw text. That's a theme that's been mentioned all through this meeting, in fact, of the importance of having encoded data. This type of algorithm lives or dies by the availability of such encoded data that can go to a rule-derived data elements for each encoded element. That's actually one of the challenges as well, as I'll get to. So again, looking at this little arrow right here, how do you solve the problem of getting your one LIS back to the multitude of LISs that may be your vendor or not? Even if the downstream target is your vendor, it may be a different implementation and not quite your implementation. So as we know, or many of us know from the reality of running clinical systems, that building one interface gets you one interface further down the road, and you haven't solved the universal problem. There's no universal interface yet, although I really wish there were. And this brings up one possible avenue of how to solve that. This was a demonstration project over the past 3 years. It's actually a constitutive part of this R01 to use this architecture and this approach to be able to get the results back to anybody who's interested in receiving them. And that's LIDEX, or Laboratory Information Digital Data Exchange, with really clinical need as a motivation. The idea of out-of-the-box laboratory information interoperability between uninitiated systems. So, for example, you go to Best Buy and you buy a cordless phone. You take it home. Do you really worry about if it's going to work when you plug it in the phone socket? You don't. And this is really the kind of interoperability we need with LISs. And I'm not kidding. I mean, literally that interoperable. And we have tools like that. And, I mean, Commerce has solved this 10 years ago with web services, or things called service-oriented architectures, and specifically XML, and specified data types. A universal code, for example, for a CBC, or a way to describe it, plus the reference interval. And you say, oh, we have LOINC. Well, actually, LOINC is about 75% of the way there. There's a need for more refinement of that. So we're on the way. But, I mean, the problems are not solved yet. We hope they will be. What we really lack here is standards. There are a number of pathologists who've been very involved in standards. In my past life with DICOM, I have been. John Gilbertson, who's one of the co-organizers of this meeting, immensely involved in HL7 as well as DICOM. But we're still not to the point of having interoperability for lab information system discrete data, lab indices, reference intervals. And then you multiply that by the reality that some parts of the world are enlightened and use SI units, and in the US we don't. And that adds an added twist to things. And so we've really, until LIDEX, not had any public attempts to demonstrate interoperability. So it remains largely an unmet need. So what the demonstration projects over a number of sites, working in partnership with the NCI, the former precursor of this meeting, Lab Infotech Summit for 2 years, was really just a partnership of vendors, academia, and government. We did the interoperability or connectathons on the exhibit floors, and a number of vendors, 6 vendors, were able to show real-world interoperability of lab results from one system to another through a common grid architecture. It worked beautifully. The idea being, you could be on one system, excuse me, you initiate a query, it goes to the cloud sends it to all the federants, basically saying, do you have it, do you not have it? And if there is information, it goes back, and then it can go to the ripple down or rules engine for additional processing if necessary. Again, you wouldn't want to put these rule engines in each disparate lab system because the oversight and stewardship of that is immense. The stewardship of just one system alone is significant, but to try doing this everywhere would be too much work. So there's tremendous value in having these complex rule engines in exactly one place, which would be a central rules server. And I should just mention that when everything is done, it goes back to the cloud and then back to the originating requesting site. You can aggregate data, or you can request that data be processed. To show you the utility of this, we used the internet. So the ripple down server at that time was in actually Sydney. And to the user, this is a completely seamless experience. Queries from anywhere in the world through our central node in Ann Arbor to Sydney back, even to Ireland, less than a second. So a federated model that's distributed over the globe doesn't necessarily impart bad performance. And then looking at the overall data model that's associated with this, the parameters need to be obviously shuttled around electronically. We don't have at this point a standard inbound HL7 interface, and as I mentioned, LOINC is not really fully normalized. So XML really is the solution. Are we there yet? Absolutely not, but we will be in a short period of time with some additional work, which is part of this project. And this is so-called harmonization, the ability to take a rules engine like this and make it available to any laboratory. That will be carried out at the vendor level, standards, professional organizations. And this is an opportunity for me to plug the Association for Pathology Informatics itself. We have a standards group. So for any of you who aren't members, please join if you're interested in encoded data, just for the encoded data opportunity's sake itself. I think this is a wonderful opportunity. This gives you a sample of some of the XML that can take from these discrete data. It's not human readable. That's okay. It's in English, but it's markup language. But from a computer perspective, it's fully normalized. And next steps with this project would be to validate this across disparate lab sources, which we've started. We're doing that with the VA using the federated model. And then an extension of the utility to other diagnoses that we know work. We know that it works for sepsis. We know that it works for detecting very early hepatocellular carcinoma, for chronic C. diff carrier status. And we have pilot data for about 25 additional diagnoses. And our statistician tells us that the tail of this detection curve, just for the and we're not even looking at anything past CBC Chem 20 at this point, probably over 1,000 diagnoses. So I think this is a very interesting period for reactivating, re-elevating the importance of these simple tests in encoded fashion. It's much more work than any one site can do. And I hope anybody who's interested, please contact us. We're definitely looking for collaborators because this is a huge body of work. And I'd just like to recognize my team at Michigan, Peter Higgins, Jeff Sika, John Hamilton, the NCI, Ian Four, and then my colleagues at Pacific Knowledge Systems, actually Rob Mansers in the audience back there. And thanks very much.
So I'll ask our next speaker, John Gilbertson, to come up and load his talk. We'll take 5 minutes here for anybody that needs a bio break or a primal scream. And in 5 minutes,